All right, guys, so today we're going to look at related rates and begin to figure out how, when we've got multiple derivatives, we can work those together. So before we do that, let's just quickly review how we did a second derivative here in our bell work. So if you haven't done it yet, I suggest you pause the video and then I will go through it with you. So if we're going to take the derivative of this and we're taking the derivative with respect to x, that means anytime we do y, we're going to have to take the derivative and then do y prime. This is then going to be equal to 2x. Because this is the derivative with respect to x, I don't need to worry about having an x prime here. And then minus 4. Now, in order to solve it, we just have to divide everything by 2y. Now, when we do that, we can see that there's a common factor of 2 here. Just to make it very, very obvious, we'll rewrite it this way. And then we can see, yes, that 2 will indeed cancel. Now, from there, what we're going to do is take the second derivative. So we're just going to take the derivative of what we already have here. So y prime is x minus 2 over y, and we're going to take that derivative. So let's go ahead and do that right here, where we're going to have y double prime, because the derivative of y prime is just 1 y double prime, equals, now we got to do a quotient rule. So low d high, which is 1, minus high d low, which is y prime, all over y squared. Now, we're kind of done, but if a better way would be to take this, which is y prime, and plug it into there. So we're going to get y double prime is equal to y minus x minus 2 multiplied by x minus 2 over y. And then the whole thing's over y squared. Now, this fraction here already has a denominator of y. This one has a denominator of 1. So we're going to want to change that so that we can get it to be a common denominator, so we can simplify these fractions. So what we're going to do here is multiply by y over y, and that'll get us the common denominator, because then we'll have y squared minus, and if you look here, x minus 2 times x minus 2 is also just going to be the same thing squared. And now that is all over y. Now, instead of dividing by y squared, remember that if we have a fraction of a fraction, what we can always do is we can take this second fraction and we're going to keep, change, flip. So this one goes up there. And so our final answer, therefore, is going to be y squared minus x minus 2 squared all over y cubed. And that would be our final answer there. All right, so let's take a look at related rates, how these are going to work. Let's jump into today's lesson. So we're going to implicitly differentiate a bunch of these different formulas, and then we're going to state what the rates represent. So if I differentiate this here, I would simply get a prime equals, I'm just differentiating r squared here, so that's going to be 8 pi r, because the 2 comes down. But then because I took r and I'm doing it with respect to time, this is going to be r prime. Because these are always with respect to time, pretty much any time we're doing this, we're going to have to write r prime here. Now, another way that we can write it to help us kind of remember, and you don't have to change it, but we can write dA dt and use this notation. And it just kind of reminds us, right, we're doing this with respect to time, that's why I have to write it. And in this case, dA dt is simply going to be the change, well, let's call it the rate of change, the ROC of area with respect to time. And dr dt is basically the same thing, except it is the ROC of radius with respect to time. And so you can kind of see how these are going to go. Whatever it is that we're taking the derivative of, it's going to be with respect to time. So it's the rate of change with respect to time. So let's take a look at the next one. Now we're doing volume of a sphere. So that's going to be dv dt is equal to, the 3 comes down and cancels with that third. So 4 pi r squared dr dt. Now, dr dt hasn't changed. This one's going to be exactly the same, the rock of the radius with respect to time, or the rate of change. And dv dt, on the other hand, is new, so let's write out what that one is. dv dt is going to be the rate of change of volume with respect to time. All right, one second. There's a bunch of construction. I'm going to go ahead and close my door. All right, so hopefully you're starting to see a bit of a pattern. Now this one, we're going to change it up a little bit. We're going to make c a constant. We're saying that it doesn't actually change, okay? So that means that when we take the derivative of this, first of all, let's think of this as being a is c squared minus b squared all to the power of 1/2, okay? So that's going to be, let's switch notation as well to practice. So we're going to do a prime is going to be equal to 1/2 times c squared minus b squared to the power of negative 1/2 times the derivative of the inside. And this is where you got to be careful. C is a constant, so it's just going to be negative 2b prime. Now, if you're doing this with me in class, you know that we don't ever write it this way. We usually actually just go straight to our simplified answer. And so a prime, the 2's are going to cancel here. And we're going to get negative b prime over the square root of c squared minus b squared. And you probably went straight to that if you've been doing them a lot in class with us. Now, b prime is going to be the rate of change of b with respect to time. Okay, and our a prime is simply going to be the rate of change of a with respect to time. Okay, now we don't have it, but if we had found c prime, because it's a constant, it would be 0, right? Because the rate of change of a constant is 0. All right, so now we're going to look at this one, and this is the volume of a cylinder, and it makes sense if you think about this like filling up liquid or something in a cylinder. The radius isn't going to change, but the volume and the height could if we're measuring the liquid inside of, say, a cup or a water bottle. So r would be a constant. So in that case, we're going to get v prime is equal to pi r squared. This is all just a fancy constant times the derivative of h, which is 1h prime. And h prime is going to be the rate of change of height with respect to time. Now volume we've already done, but we'll write it again anyway. The rate of change of volume with respect to time. Okay? Now the next one here, we're going to start working out with trig, which I know a lot of you don't like, but we got to use trig. It's super helpful, and so it's going to come up quite a bit. Okay, so we can figure out here how fast this angle's changing. So what we're going to do is we're just going to differentiate. So it would be negative sine theta, but we took the derivative of theta with respect to time. So we got to use d theta dt, or theta prime, whichever one you're using. Now here, 1 over 15 is just a fancy coefficient. So this is literally just going to be dx dt over 15, okay, or times 1 over 15, depending on which notation you used. I would write probably x prime over 15, or this way, dx dt times 1 over 15. Now, our dx dt is simply going to be the rate of change of x with respect to time. I hope by now you're finally getting the pattern. It is always the same, right? Now, d theta dt, or theta prime, just to keep us on the toes that like these are the same thing, this would be equal to the rate of change of theta, or the angle, okay, with respect to time. Oh man, it's a lot of writing. Okay, now we're going to do the volume of a cone. Now the interesting thing about the volume of a cone is with a cone, unlike the cylinder, the radius and the height are going to change as the volume changes. So as this thing gets bigger, right, if you imagine like dumping out like a pail of sand or something on the ground, it forms a cone. And that cone gets bigger by radius, height, and volume all at the same time. Not necessarily at the same rate though. So when we differentiate this, we're going to get v prime is equal to, and now because we've got r squared h, we have to do a product rule. So it's going to be 1/3 pi, because that's just the coefficient, times 2r, r prime, h, plus 1/3 pi r squared, h prime. Because in this case, the h went away. Over here, the r squared became 2r, r prime. All right, now, we've already done h prime, we've already done v prime, we've already done r prime. You should know what all of these things are by now, but just in case, rate of change of volume with respect to time, rate of change of radius with respect to time, and rate of change of height with respect to time. All right, let's see if we can actually apply this then to a scenario. So what we're going to do is, I'm going to read it the first time, and then we're going to go back and we're going to write in the margins. And I suggest you do this too, whether it's highlighting or not. You still should write in the origin or the margins about what these things are. So air is leaking out of an inflated balloon in the shape of a sphere at a rate of 230 pi cubic centimeters per minute. At the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? So again, air is leaking out. That means negative. In the shape of a sphere at a rate of 230 pi cubic centimeters. So that would be like my v prime, because it's a rate, and the hint, of course, is cubic centimeters. It's volume, okay? At the instant, the radius is 4 centimeters. So that's just my radius. What is the rate of change of the radius? So what is the r prime? All right, well, what are the variables we have? We have the radius, and we have the volume. Now you might say we have r prime and v prime. Yes, but they're technically just like a rate of that variable, so we're going to call them the same thing. Are any of these things constants? No, they're not, right? As a sphere gets bigger or smaller, so does the radius. All right, now identify the rates that are given. Well, we have v prime, which was 230, but remember it was leaking, so it's negative 230 pi cubic, I forget already, centimeters. So centimeters cubed per minute. And we're asked to find r prime, which would be, we don't know, but it's going to be in centimeters per minute. Now, the next thing we have to do once we kind of figure out what it is we're dealing with is we need to write an equation that, relates these things. So volume of a sphere, right? So the volume of a sphere is going to be 4/3 pi r cubed. And then once we've got that, we can implicitly differentiate that formula. So we're going to get v prime is equal to 4 pi r squared r prime. We just did this one earlier, so we should be able to do it quick, right? Then what we're going to do is we're going to substitute everything we know. Well, we know the volume, or v prime, sorry, is negative 230 pi. We also know that this is happening at the instant that the radius is 4 centimeters. And we're solving for r prime. So what this means is we're going to have to move all this over. So we're going to divide, and I'm going to do this at the same time, because I think you're smart, you can handle it. 4 times 4 squared. Well, that's 4 times 4 times 4, which is 64. So we're going to divide by 64 pi. And if we do that, this part all cancels out. The pi on this side cancels out. And we're going to be left with r prime is equal to this. And let's go ahead and start reducing that. So we can get negative 115 over 32. Can't reduce that by 2 or 3 or 4 or 5 or 6 or 7 or 8. I don't know if we can reduce that, so let's just leave it. And of course, that would be in centimeters per minute, as we said earlier. All right, let's try this again, okay? A little bit different scenario. We got a stone, we're dropping it in a calm body of water, causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area disturbed? All right, well, before we even write in the margin here, let's think about this. We've got radius, and we've got area, right? Now let's go find those. So the radius of the outer ripple is increasing at a rate of, so this is r prime. When the radius is 4, at what rate is the total area? So we're trying to find a prime then. Are any of those constant? No, none of those are constant, right? If the circle gets bigger, so does the radius. Are there rates that are given? Well, yes. R prime is given to us as 1, I forgot the units already, foot this time, foot per second, and the a prime we're trying to find, and that's of course going to be feet squared per second. Now we need to write an equation for a circle, because that's what relates an area and a radius. So area is going to be pi r squared. So then we can differentiate that, which is a prime to pi r prime. And then we're just going to plug in what we know so that we can find that a. All right, so then we're going to plug in all the things that we know here. So the area is the one we're trying to find, a prime. And we know that this is happening at the moment when the radius is, I forget, when the radius is 4. Okay, so our radius is going to be 4, and it's increasing at a rate of 1 foot per second. So a prime is going to be just 2 times pi times 4 times 1, or 8 pi, and this one was in feet squared per second. All right. Let's keep going. Now we're going to do that cylindrical tank. Now remember, on the cylindrical tank, we are going to have something that isn't changing this time. So let's try and do this all at once. As we read it, let's write out what these things are. So water is leaking, negative, out of a cylindrical tank at a rate, that's going to be a prime, of 3 cubic feet per second. Well, cubic feet, that's going to be volume prime. If the radius of the tank is 4 feet, that's radius. At what rate is the depth of the water, so h prime, changing at the instant during the leak? Okay, so we've got radius. We've got height. We've got volume. And this time the radius isn't going to change. The radius is just 4, always in a cylinder. It's not ever going to change. Identify the rates. Well, we have that V prime was negative 3 cubic feet per second, so feet cubed per second. And we're supposed to find h prime, which is going to be in feet per second. Write a formula. Anytime we have a prism, which a cylinder is just a prism, it's just going to be the area of the base, pi r squared, times the height. And in this case, the next thing we're going to do is it talks down here that we are going to substitute any value that represents a variable in the constant. So in this case, it's v equals pi 4 squared is simply going to be 16 h. Then we're going to implicitly differentiate this. So v prime is equal to 16 pi h prime. Then we're going to plug in the things that we know. So in this particular case, they gave us v prime. So that's going to be negative 3 equals 16 pi. And we're looking for our h prime. And so all we need to do here is, of course, slide these over. And so those cancel. And so h prime is going to be negative 3 over 16 pi. Apologize, I know that's a little messy up there, but there you go, that one's a little better. Okay, so easy enough, I think, I'm hoping. So let's do, I think we've got one more here where we're going to do it with the kind of scaffold here, and then we're going to try and do it without some. So a cone, okay, has a diameter of 10 inches. All right, let's, like we said, let's write out these things as we get them. D is equal to 10, but realistically, that means the R is 5. Right? We might as well do that because we don't usually use diameter except in circumference, and even then we often just do it as 2 pi r. So let's use r. The height is 15, so that's the height. Water is being poured into the cone, poured in, that's going to be positive, so that the height of the water is changing at a rate of, so h prime is 1.2 inches per second. At the instant, back to our like instant, the radius of the exposed surface area of the water is 2 inches. So the radius is 2. At what rate is the volume prime, of the water changing? So we have radius, we have height, and we have volume. None of those things are remaining constant with a cone. Identify the rates that are given. Well, we got that h prime is equal to 1.2 inches per second. And we need v prime, which is going to be in inches cubed per second. Now what they didn't give us is r prime. That's a bit of a problem. So I'm going to come back to that in a second, but let's look at this. So we need a formula. Okay, so then we need to relate all of those things. And so the volume of a cone is simply going to be V is equal to pi r squared h over 3. Okay, because anytime we've got a cone pyramid, it's just a third of the prism. All right. Now, the issue we have here is that we do not have r prime, right? We didn't get it. We have nothing to do with it. And so if you look here, it is important to keep in mind that you can have only one more variable than you have rates. You may have a make a substitution that relates one of them to get rid of it. So we need to get rid of r because we need to find v prime and we have h prime. So r is the problem. Now, luckily with a cone, we have this relationship that r over h is always going to be the same. And in our particular case, for this one cone, it is 5 over 15, or 1/3. Now, I can then use that and solve it to figure out what r is. This allows me to make a substitution. So I multiply both sides by h, and I get r equals h over 3. I can then make a substitution, just like when we've done systems of equations, and I can eliminate it. So then I'm going to get v is equal to pi, and instead of r, I'm going to get h over 3 squared times h over 3. Okay? Now, from there, let's see how good you guys are here. My volume is literally just going to be pi. H squared times h is h cubed. And then 3 squared is 9 over 3 is the same as like times another third. So it's going to be that this whole thing is just over 27. Now I see that that's really hard to read. So let's rewrite that before we go ahead and implicitly differentiate. So there it is. Now we're going to implicitly differentiate. So v prime is equal to 3 pi h squared h prime over 27. But I can cancel out that 3 to be 1 and the 27 to be 9, because 3 over 27 is the same as 1/9. Then I'm going to substitute in my values. So I'm looking for v prime. So I'm going to get pi h. We don't know what h is. We know the radius, right? It told us the radius was 2, right up here. But we can use the radius to solve for h, because we know that r is equal to h over 3 in this particular cone. And we know that the radius is 2. So 2 is equal to h over 3, which means that h is just 6 when we multiply the 3 over. So then we get 6 squared times h prime, which I believe was 1.2. Let's go make sure. Yes, it was. And that's all over 9. So v prime, therefore, if we simplify this, 6 squared is 36. And then I can multiply that by 1.2. That's a pain. I'm going to divide it by 9 first. So 36 divided by 9 is 4. And 4 times 1.2 is easy. That's 4.8. So we get 4.8 pi. And that one is in inches cubed per second, I believe. But let's go make sure. Yes, inches per second. So inches cubed per second for the volume. There we go. Excellent. Now, what we're going to do now is we're going to take away the kind of framework that I built, and we're going to see if we can do it without it, which means we may need to draw a picture, we may need to kind of remember those steps and go through it. So we have a ladder that is 25 feet long, leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. How fast is the top of the ladder moving down the wall when the base of the ladder is 7 feet? Okay, before we can't even really do our whatever, because this time we just have a ladder against the wall. So let's draw a picture and see if that helps us kind of figure out what's going on. Okay, so now that we have a picture, we could think of this as oh, this is like a triangle. So let's go ahead and label it like A, B, C. See if that helps us. Now the ladder is 25 feet long and leaning against it. So this would be 25. So in other words, C is 25. Okay. Then the base of the ladder is pulled away at a rate. So that's not A, but it is being pulled away. So that would mean that A prime is 2 feet per second. It's going to the right. So that's positive from physics. We hopefully remember that. How fast is the top of the ladder moving down the wall? Well, that would be like B prime. Right? How fast is this changing? That's the thing we want to know. And we're doing it when the base of the ladder is 7 feet from the wall. So when A is 7. Okay, well, we can relate those. That's just Pythagoras. So A squared plus B squared is equal to C squared. Excellent. Now, before we differentiate it, remember we plugged in any constants. Well, in this case, the ladder doesn't change size, so it's just 25. Now we can differentiate. And we get 2AA prime plus 2BB prime equals 0. Now the issue is if we go and start plugging these things in, we're going to see that we don't have B. We need to find B to do this. But luckily, we have a triangle, and we can just use Pythagoras at the exact instant when A is 7. And so what that means is that C squared minus A squared is going to be equal to B squared, or B is equal to the square root of those. So B is going to be equal to the square root of 25 squared, or 625, minus A squared, or 7 squared, or 49, and that's equal to B. If we subtract those, that's going to give us 576, and the square root of 576 is 24. All right, so now we've got everything we need. So we can plug it in. 2a is 7, a prime is 2, b is 24. We just solved for that one. And b prime is the thing we're looking for. So then we can simplify all these, move it over, solve for b. So 2 times 2 is 4, times 7 is going to be 28. 2 times 24 is 48, b prime. Then we're going to go ahead and move that over so that we get 48 b prime is equal to negative 28. And then we simply divide in order to get what b prime is. Now we can reduce that. We can divide both of these by 4. So 28 divided by 4 is negative 7. 48 divided by 4 is 12. And the only thing left would be our units. So this is b moving down, so it would be feet, it's the height, per second, since we are in seconds here. And there we are. Now, if we take a look at the next one, we've still got the triangle formed by the house, the ladder, and the ground. We want to find the rate at which the area of the triangle, so this time the rate at which the area, that's a prime, is changing when the base of the ladder is 7 feet. Okay, so this is still the same situation. A is still 7. So we can use all of the information we just calculated in this particular problem still. We haven't changed anything. If we changed how far away this is, well, that's going to change everything, right? So we need to go ahead and recalculate it. But because this one is the same, we know that A is 7, we know that A prime is 2. Over here, we know that B prime is negative 7/12. We know that B is 24, and we know that C is 25. And we want to know the area. Well, the area is going to be, in our case here, equal to A times B divided by 2. So that's a little bit awkward since the way we did this. So why don't we change our labels? Let's change A to being the base. And let's change B to being H for the height. Because we're used to being area is equal to 1/2 base times height. And I think that's going to make it easier for us. And it doesn't matter what we call these. We can call them anything we want. So now if we differentiate here, we're going to get A prime is equal to 1/2. We got to do a product rule. So we're going to get BH prime plus 1/2 B prime H. And then we just plug in everything we know. So A prime is what we're looking for. B is 7. H prime, our height there, is negative 7/12. And then our B prime is 2. And our H is 24. Now the 2 and 1/2 cancel there. And so we get that A prime is equal to negative 49/24 plus 24, which really, if we want these to be the same, that's going to be negative 49 plus 576 all over 24. Because remember, we did that earlier, right? 24 squared is 576. And then we can just simplify what that is. And that's going to give us, let's see here, 527/24 is our A prime. You know what? I didn't give it units. Let's give it units. Our area, so it's going to be feet squared per second equals A prime. There we go. Better. All right. So now what we're going to do is we're going to find the rate at which the angle formed by the ladder and the wall in the house is changing. So angle, we're going to have to add something different. When the base of the ladder is 9. Okay, so if this is now our B, we've now changed things, right? So we cannot use anything that was not given to us in the original problem. The ladder is still 25, but now B is going to be 9, and we know that B prime is still going to be 2. But all this information over here we can't use. But we may not need it, so let's wait. Now we want to find the rate at which the angle, theta, we'll call it, formed by the ladder and the wall. So that's this guy here. So we want to know, basically we want to know the rate at which the angle formed by the ladder and the wall is changing. So that's like theta prime. So what relates this angle, the opposite side, and the hypotenuse? Now I hope you're saying sine. It is. So sine theta is going to be equal to 9/25. Perfect, right? But we shouldn't do it as 9 because 9 needs to be B, right? We need it to be B for now so that we can actually take the derivative. Neither of these things are constant. The only constant is the 25, right? So that's why I can put it in. So then I can take the derivative. The derivative of sine is cosine theta. But if I took the derivative of theta, which is not time, then I would need theta prime. And then I'm going to get b prime over 25. And so then all I need to do is divide both sides by cos theta. And if I do that, I will get what theta prime is. And we know that b prime is 2. So we're going to get 2 over 25 cosine. And here's the problem. We don't know theta yet. But it's okay because we can find it easily from this original thing that we did. So we can say sine theta is equal to 9 over 25. And then we can just solve it by doing the sine inverse, right? So if we take the sine inverse of both sides, theta is going to be equal to sine inverse of 9 over 25. And then we just need to put that in our calculator. And so if I put that in my calculator, I will get sine inverse of 9 divided by 25. Make sure it's in radians. And I will get 0.368. We'll use 3 decimals because the College Board usually uses 3 decimals. I know, I'd rather use sig digs, but they don't, so we don't. And so in this case, theta prime is going to be, sorry, I need to plug that in. So this cosine theta is 0.368. So then we just put this into our calculator and we get 2 divided by 25 times the cosine of 0.368 radians. And we get that theta prime is equal to 0.0857, so equals 0.086 rads per second, because it's how many radians it's changing. Excellent. All right, we're almost done. We got just a couple more examples here for us to try. So we're going to have an airplane that is flying at an altitude of 5 miles and passes directly over a radar antenna. When the plane is 10 miles past the antenna, the rate at which the distance between the antenna and the plane is changing at 240 miles per hour. What's the speed of the plane? Okay, let's draw a picture and then we can start figuring out what those things are. So we have a plane above an antenna. So let's put a point here. Let's call that our antenna. We know that this is going to be 5 feet above. Okay, and up here, it doesn't really matter. Let's just call that point B. And then we want it to be 10 miles past the antenna. It doesn't matter which side we do it on, and we'll call that point P. Now, we know that it is 10 miles past, it's 5 miles up in the air, and we know the speed of the plane. So if we think about this, let's write some of these things down. This is side A, this is side B, this is side P, because we always label them with the opposite, right? So lowercase of the opposite vertice. Now, if we look at this, we know that P is 5, and we know that it's not changing, it's a constant. P prime is not going to change, it's not going up and down. Now over here, on the other hand, A is going to be 10 and A prime is 240 because it tells us it's going 240 miles per hour. So what we need to know is how fast B prime, oh, hang on. No, that's not, this isn't 240. I did that wrong. At the rate at which the distance between the antenna and the plane is changing. Sorry, so B prime, my apologies, is 240. And we want to know what A prime is. My bad. Okay, now what we're going to need then is, in order to find that, we're obviously going to have to use Pythagoras with all our sides, and I'm going to need to find B. So let's do that first. Okay, so B is the hypotenuse, so it's going to be equal to the square root of 5 squared, 25, plus 10 squared, 100. And so B is going to be the square root of 125. And we know that B is going to be 5 root 5 if we're good at reducing radicals, which hopefully we are by this point. All right, so then we can go back and do our original Pythagoras to relate all these things. So that would be B squared is equal to A squared plus P squared. All right, but remember we plug in the things that are constant, so it's B squared equals A squared plus 5 squared, because the height is not changing. Then we can differentiate. So we get 2BB prime equals 2AA prime plus 0. So that just goes away. All right, now we plug in what we know. So if we look at this here, we know that B is 5 root 5. B prime is 240. And over here, A is going to be 10. And a prime, the speed of the plane, is the thing we're looking for, so we're going to divide both sides, therefore, by 20. So these cancel, because 2 times 10 is 20 over 20. And over here, we can reduce this a little bit too. Probably the easiest is 20, like 240 divided by 20, which is going to give us 5, 10, 12. So then if we multiply all that together on this side, we're going to get 2 times 5 is 10 times 12. It's going to be 120. Square root 5 is equal to a prime. But let's go ahead and let's write that better. So let's write this with our units, and that's going to be miles per hour. And so that is going to be our a prime, how fast the speed of the plane is going. Now, realistically, that's kind of a strange number. So in this particular case, when we're dealing with some like real life scenario, it's often a good idea to round it. So let's go ahead and go 120 times the square root of 5, and we will get that that is 268.328 miles per hour for a prime, or the speed of our plane. Awesome. All right, almost there. The radius of the sphere is increasing at a rate of 2 inches per minute. Find the rate of change of the surface area of the sphere when the radius is 6 inches. All right, so next one here is we're going to take the radius of a sphere. It's increasing at a rate of 2 inches per minute. Find the rate of change of the surface area of the sphere when the radius is 6. All right, so in this case, we got a few things to kind of point out. It's increasing, meaning it's positive. So this here is going to be our r prime then. Find the rate of change of the surface area. So we want to know a prime. So the only thing that we can do to relate a and r of a sphere is to say that the area is equal to 4 pi r squared. And this gives us the surface area of a sphere. Then we can go ahead and we can differentiate it. And so we get a prime equals 8. 2 comes down, we get 8 pi r prime. Then we just plug in what we know, which we know the radius, sorry I forgot to write that part, is 6, and that the r prime is 2. So a prime is going to be 8 pi times 6 times 2. And so finally a prime is going to be, let's see here, 12 times 8, 96 pi. And that would be in inches squared per minute. All right. All right, very last one we got here. This is where we're going to have to pay a little bit of attention because it's going to be doing some jumping from one formula to another. So let's take a look. We got a spherical balloon and it's expanding, so positive, at a rate of, so this would be my v prime, 60 pi cubic inches per second. How fast is the surface area of the balloon expanding? So that would be like a prime, or SA prime if you want, for surface area. When the radius of the balloon is 4, so we got a radius. So if we think about this, well, we can't actually connect V and A, but we can connect V and R and A and R. So R is going to be like our go-between. So the formula for the volume of a sphere is going to be 4/3 pi r cubed. And the formula for the area of a sphere, as we know from the last question, is 4 pi r squared. Now, you can kind of start to see what's happening. If we have V prime, we can solve for R prime. Then we can use r prime in the area formula to solve for a prime. So that's what we're going to have to do. So here we're going to take the derivative and get v prime is equal to, the 3 comes down and cancels with the third, so it's just 4 pi r squared r prime. And then we know that v prime is 60 pi. And we know here that our radius is 4. So that's 16 when we square it, r prime. And then, of course, we're going to divide both sides. And if we look here, 4 times 16 is going to give us 64. So we're going to divide by 64 pi on both sides. And we can see here that a bunch of that cancels, right? Our pi cancels. And so our r prime is going to be 60 over 64. Let's start reducing that. So 30 over 32, which would be the same as, 15 over 16. All right, so our r prime is 15 over 16. Now what we can do is we can take this and we're going to plug it into the other formula over here once we differentiate it. So when we differentiate the area, it's a prime is equal to 8 pi r prime, just like we did in the last question. But now we know r prime. So we can say, well, A prime is equal to 8 pi times 4 for the radius times 15/16 for our r prime. That's the rate at which the radius is growing. And then we just simplify that. So 8 times 4 gives us 1632. 32 over 16 gives us 2. And then 2 times 15 is 30. Now, just in case that was a little too fast for you, I'll write it out here. So 8 times 4 is 32 pi, and then 15 over 16. Then what I'm doing is I'm reducing this, because 32 over 16 is the same as just 2. And so that gives us that it's 2 times 15, which is 30 pi. And that would be in inches squared per second in this case. And so that would be our final answer. So this is going to be a question that I see a lot, you guys, particularly in the College Board, so I will always put it on in my stuff, because they want you to be able to realize that, hey, you can find r prime, use r prime to go between, and use that as the common factor between the volume and the area. So you got to make sure you know how to do that, all right? And that's it, guys. All right, we'll see ya.